You remember that our goal for the week is to solve the harmonic oscillator in quantum mechanics, right? And so we have the harmonic oscillator with a potential energy, right? That is V of X is 1/2 m omega squared x squared, right? That this combined variable is our spring constant K. And so this goes into the Hamiltonian, right? So the Hamiltonian is minus h bar squared over 2m times this second derivative with respect to x plus the v of x, right? So plus v of x. And now we want to solve the equation, and I'll put a hat because it's an operator. We want to solve the equation. Hamiltonian acting on psi is equal to E psi. Okay, so this is the time independent Schrödinger equation. And that works for figuring out the special separable solutions. Okay, so I told you that one tricky way to solve this would be to do stuff with operators. And so I spent about an hour yesterday telling you stuff about operators, okay? And so now you're wondering, what does this have to do with solving the Schrödinger equation for this problem? Okay, so let's see if we can get to that today. All right, so you remember at the very end of the last class, I defined an operator, I defined a pair of operators, A plus and A minus. Okay, so I'll say, we defined these operators, A plus and minus, which look like this, the 1 over square root of 2h bar m omega, then minus or plus I p hat plus m omega x hat. Okay. And so in this notation, the plus or minus here corresponds to the minus or plus there, right? So this is two equations in one, right? So the top sign there goes with the top sign there, and the bottom sign there goes with the bottom sign there, okay? And also, in this notation, the operator P means minus I h bar d by dx. Okay, so up here in the Hamiltonian, this is a p squared over 2m plus v of x, right? Or it's a p squared over 2m plus 1/2 m omega squared x squared. Okay, so now that we've got these nice operators, what can we do with them? Okay, so let me show you. Okay, so suppose we want to compose them. Okay, so we want to make the combination whoops, no, do the minus first. A minus A plus. Okay. So this is a composition of operators. That means that this pair of operators, can operate on any function that comes along, right? So if we have a minus a plus acting on some function f, it means that the function f goes into a plus, and then the output of that goes into a minus, and then that produces a new function f new, like that. Okay, so suppose we want to figure out what is this combination. Okay, so let's try to multiply this out and simplify it. Okay. So you know what you would do if this were ordinary multiplication, right? If it were ordinary multiplication, it would be like one binomial times another binomial, right? So it's what you learned in high school algebra. Okay. Now for operators, it's kind of similar to that, but we have to make sure we keep the right sequence of the operators because these things don't commute, right? It matters what order they go in. Okay, so if we have the combination a minus a plus, like that, okay, that means 1 over the square root of 2h bar m omega. Now, a minus is I p hat plus m omega x hat. Yeah? And this is acting on the output from a plus, which is 1 over 2h bar, m omega, and a plus is minus I p hat plus m omega x hat, like that. Okay, so we want to simplify this. Okay, so one thing that you can see is that these things are linear operators, right? Remember that was one of the principles we talked about yesterday. So that means that multiplication by a constant, that can just be pulled out, right? That an operator acting on a constant times a function is just the constant times the operator on the function. So this factor of 1 over the square root, that can just be pulled out in the front. No problem with that. Okay, so we have in the front 2 factors of that square root. So it gives us 1 over 2 h bar m omega, like that. Okay, then it's this combination of pairs, minus I p hat plus m omega x hat. Okay, so when we're composing operators like this, we can expand, like expanding the product of binomials, but we have to make sure in every single term to keep the sequence of p and x the same, because these things don't commute, right? That the sequence matters. So we can multiply them out, compose them out. Okay, so let's say first we have this IP composed with this negative IP. Okay, well, the factor of negative I gets pulled out, right? It just is a constant. Okay, so the negative I gets multiplied by the I, that makes 1. And we have then a P operator squared. That means you have the P operator acting 2 times. Okay, now how about the first thing here acting on the second thing? So this gives us plus I m omega, those things are all constants, p x, okay, that sequence. Now, what about this second acting on the first? Okay, that gives us negative I m omega x p. Right? And so you can see that the x is on the left and the p is on the right in this case. Okay, so these two terms don't cancel, right? Because it matters what sequence you have them in. Okay, and then the last term in here, this is m omega x hat, and here's another m omega x hat. Okay, so that gives us a plus m squared omega squared x hat squared, like that. Okay. So, anytime the idea is anytime you have this pair of operators acting on some test function over here, that gives you the same thing as this sum acting on the test function over there. Okay, you sort of good with that? All right. Okay, now let's see if we can simplify a little bit. Okay, so one way to simplify is, well, when things are added up, we can change the order of the things that we're adding. Adding is still commutative. Right? So this is 1 over 2 h bar m omega. Let's see, there's a p squared. I'll add in 1 over m squared omega squared, like that, and x hat squared. Okay, and now what? Well, now we have plus I m omega, and then there's a combination, px minus xp. All right. Now, let's look at this. Okay, so the px minus xp, this is the commutator, as we were talking about yesterday. Okay, this is exactly what we mean by the commutator of p and x, right? It shows just how much they fail to commute, right? How much it matters what the sequence of those operators is. Okay, so that is something that we worked out yesterday, okay? And we already derived, I'm just looking at my notes, that this commutator is equal to negative I h bar. Okay, so then we can do a little bit more simplification, okay? So we can say this is 1 over 2 h bar m omega p squared plus m squared omega squared x squared. Okay, and now the I and the negative I cancel, and we can say just plus h bar m omega. Okay, looking a little bit simpler now. Okay, so next, the next simplification that I want to do is I want to take the 2h bar in the denominator here and put it inside, no, not the 2h bar, excuse me, the 2m. I'm going to take 2m and put it inside the parentheses. Okay, so the 2 and the m, and those things are going to go inside the parentheses on each term. Okay, and then this all simplifies to 1 over h bar omega. And then we have p squared over 2m plus 1/2 m omega squared x squared plus 1/2 h bar omega, like that. And now, let's see, we can look at this and say, well, we recognize this combination. This p squared over 2m plus 1/2 m omega squared x squared. Okay, let's go back to the Hamiltonian. That is the Hamiltonian right over here, okay, for the harmonic oscillator. Okay, so that means we can relate the A plus and A minus operators to the Hamiltonian. Okay? And so in terms of the Hamiltonian, we get that this is 1 over h bar omega. It's the Hamiltonian plus 1/2 h bar omega. So that's equal to 1 over h bar omega times the Hamiltonian, all plus 1/2. Okay, so this is our combination A minus A plus. Like this. Okay. That's an interesting combination of operators, all right. Now, what if we had the A plus and the A minus in the opposite sequence? Okay, so what if I do A plus on the left and then A minus? Okay, that's going to be approximately the same as this, except for a few signs. Okay, so let's try to repeat with all the different signs. Okay, so A plus, A minus. Okay, so that is 1 over the square root of 2h bar m omega. And here you have the negative I p plus m omega x hat, and then there's another square root. And then IP plus m omega x hat. Okay, I'm going to repeat stuff, but I'm going to do it more quickly this time because it's very similar to what we just did. Okay, so the square root comes out. Okay, so we get 1 over 2h bar m omega. And now if we expand the pairs, okay, so we get the first acting on the first. That's p squared. the first acting on the second. Okay, so negative I m omega p etc. Okay, then the second acting on the first. Okay, so that's plus I m omega x p. And then the second acting on the second, so m squared omega squared x squared. Okay. So again, rearranging the terms, 1 over 2 h bar m omega, there's the p squared plus m squared omega squared, and now plus I m omega in the commutator of now x with p, like that, okay? And this commutator of x with p is I h bar, right? That's what we already worked out. So this combination is 1 over 2 h bar m omega p squared. Whoops, I forgot an x squared here. Oops, sorry. Plus m squared omega squared x squared minus h bar m omega, like that. And again, I'll take the factors of 2 and m and put them inside on everything. And so that's equal to 1 over h bar omega. And we get a p squared over 2m plus a half m omega squared x squared minus a half h bar omega. And once again, this combination is the Hamiltonian. So the whole thing is equal to 1 over h bar omega on the Hamiltonian, and now just minus a half. Okay, so it's very similar to what we had before, right? If it's a minus a plus, then that gives us 1 over h bar omega times the Hamiltonian plus a half. And if we have the opposite sequence, a plus a minus, that gives us a plus a minus is equal to the same thing, but with a minus a half instead of a plus a half. Okay, so one thing that we get from this is what's the commutator of a plus and a minus. Okay, so the commutator a minus comma a plus. Okay, so that means a minus a plus minus a plus a minus. So that is 1 over h bar omega Hamiltonian plus a half, that's the first thing, minus 1 over h bar omega Hamiltonian minus a half. Okay. So these Hamiltonian operators cancel, and this is all just equal to 1. Okay, so a plus and a minus do not commute, meaning their commutator is not 0. But we know what their commutator is. It's 1. Okay, and this also gives us 2 different ways to write the Hamiltonian, right? We could say because A minus A plus is equal to 1 over h bar omega, the Hamiltonian, plus a half, okay? So we can rearrange terms to get an expression for the Hamiltonian. Okay, so that is A minus A plus minus a half, right? Or that would tell us that the Hamiltonian is h bar omega A minus A plus minus a half h bar omega, like that. Okay? Or equivalently, we could say the Hamiltonian is h bar omega A plus A minus plus a half h bar omega. Okay, so these are 2 equivalent ways of writing the harmonic oscillator Hamiltonian in terms of A plus and A minus. Okay, so doing okay with this stuff so far? Okay, so you know, it's a lot of tricks with operators so far to end up with these expressions for the Hamiltonian. But now we're finally getting to the point. Okay, so remember, we want to solve the time independent Schrodinger equation, which is that h psi is equal to E psi. Okay, so we want to get what are the special solutions. Okay, we're going to have, we think there are going to be multiple solutions for some psi, and that psi will go with some energy E. Okay, so here comes the trick. Okay, let's say, suppose we know one solution. Okay, so suppose we know one solution, psi of x, with energy E. Okay, that means that the Hamiltonian acting on psi is equal to E psi. Okay, now you guys are all thinking to yourselves, what do you mean, suppose we know one solution? We don't know one solution, right? We know 0 solutions, okay? Just go with it, okay? So suppose we did know one solution, okay? Hypothetically speaking, what if we did know one solution, okay? Then let's consider this, the state A plus acting on psi, okay? This is a function, right? Instead of the state, I could say, let's consider the function, right? So that means there's some f nu of x, which is A plus acting on psi of x, right? Which means 1 over the square root, whatever that thing is, 2h bar m omega, and the, I forgot already, minus ip plus m omega x, right? All of these operators acting on psi of x, okay? So if we knew one solution, I'm going to generate another function, okay, which is this operator acting on the solution that we supposedly know, okay? And now, here's a question. Is this thing also a solution? Let's find out, okay? Is it a solution? We can tell by letting the Hamiltonian act on it. Let's let the Hamiltonian act on F nu. Okay? That is equal to the Hamiltonian acting on A plus acting on psi, okay? Because F nu is A plus psi. Okay? Now, let's use one of our expressions for the Hamiltonian. Okay, how about the second expression for the Hamiltonian right there? Okay, so this is equal to h bar omega a plus a minus plus a half h bar omega acting on a plus psi. Okay, now can we simplify this thing? Okay, well, what is this thing? Okay, this thing is h bar omega. Okay, in the first term, we have a plus acting on a minus, acting on a plus, acting on psi. I'll put the psi over here. The second term is plus a half h bar omega times a plus acting on psi. Okay, so you can see the sequence of things, right? That this is all equal to what we started with. Okay, now I can see, in each of these terms on the left, there's an a plus. Right? So I can factor that out on the left. So this is equal to a plus acting on h bar omega a minus a plus plus a half h bar omega psi. Okay. So maybe it's not obvious to you that you would go from here to there, right? But you could go backwards, right? You could go from there to here, right? You can go this way, right? Or likewise, you can go from there to here this way, right? And each of these expressions can be expanded to get this thing. So they're equal to each other. Okay, now let's look at what we have in parentheses right here, okay? This actually looks kind of like our other expression for the Hamiltonian, right? Our other expression for the Hamiltonian was this thing, okay? So what we have in parentheses right here is our other expression for the Hamiltonian plus h bar omega. So this is A plus acting on the Hamiltonian plus h bar omega psi. Okay, so this is A plus acting on the Hamiltonian acting on psi plus h bar omega times psi. But we know what the Hamiltonian acting on psi is, because that was our supposition up here, right? We're supposing that psi is already one solution of the time-independent Schrodinger equation with an energy E. So H bar acting on psi, no, not H bar, H hat, right? The Hamiltonian acting on psi is E psi. It's just a number multiplying psi. Okay? So this, oops, wrong pen. This is A plus acting on E psi plus H bar omega psi, which is, I'm running out of room, which is, I have A plus, what did I write? A plus acting on E plus H bar omega times psi, right? Because E is a number and H bar omega is another number. So E plus H bar omega is another number. So it can factor out, since A plus is a linear operator. So this is E plus H bar omega times A plus psi. But A plus acting on psi, that is F nu. Okay. So this is E plus H bar omega F nu. Okay. So you remember what we are calculating here is the Hamiltonian acting on F nu. So the Hamiltonian acting on F nu is a number times F nu. So this number is E nu. Okay. Therefore, F nu is a solution of the time-independent Schrodinger equation with an energy E nu, which is E plus H bar omega. Okay, so if only we knew one solution, we could get another solution, right? By applying the A plus operator. It would be a higher energy solution, right? That the new energy would be higher than the old energy by an increment of H bar omega. Okay. But then if we did that, we could repeat, right? We could let A plus act again, and we could get an even higher energy solution, and even higher, and so forth, right? If only we had one. Okay. You all right so far? All right. what do you suppose would happen if we let, well, here, so before I say that, then there's a name, okay? So we say, therefore, A plus is called a raising operator. That is, if we have solution psi with energy E, then that gives us a solution A plus psi with energy E plus h bar omega. Okay, let's say, well, that was pretty nice. What do you suppose A minus does to the energy? Let's find out, okay? So let's go back and repeat this calculation with A minus, okay? And again, I'll do it a little bit more quickly because it's very similar to the way I did it before. Okay, so let's now let F nu equal A minus acting on our solution psi. Okay, and we want to know if this is a solution of the time-independent Schrodinger equation. So we'll let the Hamiltonian act on this F nu. Okay, and I will choose the form of the Hamiltonian, the other one I didn't do before, which is, what is it in my notes? Okay, it is h bar omega A minus A plus minus a half h bar omega. That's one of our expressions for the Hamiltonian. And this is acting on A minus, acting on psi. Okay, so if I expand all this stuff, this is h bar omega A minus A plus A minus acting on psi minus a half h bar omega A minus acting on psi. And then I'll pull out an A minus on the left because there's one here and one there. So this is, oops, A minus acting on h bar omega A plus A minus minus a half h bar omega, and all that's acting on psi. And now we look at the stuff here and say, well, this is just like our Hamiltonian minus h bar omega, right? Because one of our expressions for the Hamiltonian was this thing plus a half h bar omega, okay? So this now becomes A minus acting on Hamiltonian minus h bar omega acting on psi. Okay. But we know that the Hamiltonian acting on psi is E psi. That's our assumption. All right, so this is A minus E minus h bar omega psi, which is, now we can just factor out that E minus h bar omega times A minus psi, which is E minus h bar omega times our F nu function. Okay. So if we had one solution to start with, then we could let A minus act on it, and we would get a new solution which has this energy E minus h bar omega. Okay, so we could say, therefore, A minus psi is a solution of the time-independent Schrodinger equation with a lower energy, E minus h bar omega. So for that reason, A minus is called a lowering operator. Okay, so if only we had one solution to Schrodinger's equation, then we could generate as many solutions as we want, right? We could hit it with A plus, it goes up in energy. We could hit it with A minus, it goes down in energy. And we could keep repeating, hit it with A minus twice, 3 times, 4 times, it's going down. Hit it with A plus, it keeps going up, right? So we could generate as many solutions as we wanted. Okay, so that means we get a ladder of energies. There is a ladder of energies and the corresponding states. So I could say, here is the state that we start with, okay? And so it has an energy of E and a wave function, just psi of x. Okay, and now I could hit it with A plus. So here's A plus psi, and that has an energy E plus h bar omega. And I could hit it with A plus again. So here's A plus squared psi, and that makes a rung on the ladder there. Okay, and that has an energy which is E plus 2 h bar omega. And so on, going up. Okay, and then I could also hit it with A minus. And this would give us an energy E minus h bar omega. And I could do that again. A minus squared acting on psi. And this would give us an energy E minus 2 h bar omega. And so on, going down. Okay, so is this still all right for you guys? Okay, questions, anything? Yeah, okay. So you can see already that one thing is a little bit different from the particle in a box, okay? Because when we had the particle in a box, the energies of the states were proportional to some integer n squared, right? And so the steps were not equally spaced, right? For the particle in a box, you had a state with energy 1 times something, or 4 times something, or 9 times something, 16 times something, right? So the spaces between the energies keep getting bigger, right? But here it's different, right? Here the energies are equally spaced. Okay, so all right, that's a difference between the particle in a box and the harmonic oscillator. All right. Now, when you see a ladder like this, okay, one natural question to ask is, can the ladder go up and down forever? Okay. So, you know, there's a dot, 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 right? Is it dot, dot, dot forever, or dot, dot, dot until you reach some limit? Okay. Well, going up, yes, it can go up forever. Up forever, yes. Okay. There is no upper limit on the energy. Right? The energy can just keep going higher and higher and higher with no limit. Okay, but what about down? There's a difference there. Down forever, no. Okay, there is a lowest possible energy. And one way to see that is that in a harmonic oscillator, you know, the total energy is the sum of a potential energy and a kinetic energy, right? And the kinetic energy is p squared over 2m, right? It's a square of something, right? It has to be positive, right? So the kinetic energy has to be greater than or equal to 0. Okay, and likewise, the potential energy is the 1/2 kx squared. That has to be positive also. So the total energy has to be greater than or equal to 0. Okay, so you can't just keep going down in equal steps forever. There must be a lowest energy state. There must be a lowest energy state that is here, okay? This is the lowest, okay? It has an energy, let's call it E0. And a wave function you could call psi 0. That is the lowest. You can't go lower than that, okay? But you can keep going up. Okay, so here it's going to be a plus on psi 0, a plus squared on psi 0, a plus cubed on psi 0. Okay, and here it's going to be an energy E0 plus h bar omega, E0 plus 2 h bar omega, E0 plus 3 h bar omega. Okay, so this ladder, right? It's a stairway to heaven, right? It has a bottom on the earth, and it keeps going up forever. Okay, but with no upper limit. Okay. So now you're wondering, haven't I contradicted myself, right? Because I told you that if you have a state and you hit it with A minus, you get a lower energy state, okay? But then I also told you there's a wave function on the bottom, okay? So you might be wondering then, well, what if I have this wave function on the bottom and I hit it with A minus? What do I get, right? We know that the wave function, yeah, what do I get? What do I get? So we'll say, what is a minus acting on psi zero? Okay. Well, we know that A minus acting on psi zero is still a solution of Schrodinger's equation, but it can't be a real quantum state because you can't have a state lower than the bottom, okay? So the only way to resolve this discrepancy is if A minus acting on psi zero is just zero, okay? So I'll say we must have A minus acting on psi zero is just equal to nothing, is equal to zero, okay? So in that case, A minus psi zero is not a state, but it does satisfy Schrodinger's equation. Satisfies the time independent Schrodinger equation in a trivial way, right? That the Hamiltonian acting on A minus psi zero is just the Hamiltonian acting on zero, which is zero. So it's a trivial solution. It's like the state for a particle in a box if the coefficient in the front is zero, right? It's a nothing. It's a wave function equals zero everywhere. Okay, so we must have that A minus acting on psi zero is zero. Okay, so now let's remember what A minus is, and then we can work out what this equation means. Okay, so remember that A minus is defined as, well, there's this square root in the front, over the square root of 2h bar m omega, I p plus m omega xl. Okay. So that means that we want to have the equation A minus acting on psi zero is zero. Okay, so let's actually work that out. Square root of 2m h bar omega IP plus m omega x operator operating on psi zero of x is equal to zero. Well, okay, so we multiply through both sides by this square root, that cancels, okay? Now we remember what the momentum operator is, right? That P is negative I h bar d by dx. Okay. So this equation is saying that I times negative I, that's 1, right? So h bar d by dx plus m omega x acting on psi 0 of x is equal to 0. Okay, so if we work this out, h bar d psi 0 dx plus m omega x psi 0 of x is equal to 0. All right. So look, this is now a regular differential equation. Okay, so let's see if we can actually solve this differential equation. Okay, so let's do it. Okay, so h bar, I guess I'll write it with regular derivatives, not partial derivatives. D psi 0 dx is equal to negative m omega x psi 0 of x. Okay, so if we want to solve that, let's see, we can multiply through, I'm going to get all the psi stuff on the left side and all the x stuff on the right side. Okay, so here it would be d psi 0 divided by psi 0 is equal to negative m omega over h bar x dx. Okay, and then let's integrate both sides. So that tells us, let's see, the integral on the left is the log of psi 0 is negative m omega x squared over 2 h bar plus a constant. And then if I take the exponential of both sides, that tells us psi 0 of x is e to the minus m omega x squared over 2h bar times e to the constant. Okay. And e to the constant is some other constant, which I can call a, right? Like the amplitude that you've done in your homework. Okay. Therefore, psi 0 of x is a e to the minus m omega squared x squared over 2 h bar. So look, we actually have a function here. Okay. So this is a function for the bottom rung on the ladder.
Dr.
Right.
Salinger,
Please.
did you mean to put a square on omega?
No. Thank you. Aha. Very good. Thank you, Andrew. M omega x squared. Okay, much better. Good, good. Okay, and now we could say, what's the energy? signal E0 corresponding to psi 0. Okay. Well, one way to work that out is from Schrodinger's equation. Okay, so I could say, let's let the Hamiltonian act on psi 0, and that'll tell us what is E0 times psi 0. I could totally do that, but it actually is work because you have to take derivatives of this exponential thing. There's a trickier way to do it, okay? The trickier way to do it is another trick with operators, okay? The trick with operators is to use our form for the Hamiltonian, okay? So remember that the Hamiltonian, this is equal to h bar omega a plus a minus plus a half h bar omega, right? That's one of our expressions for the Hamiltonian. And this is acting on psi 0, okay? And this is h bar omega a plus acting on a minus acting on psi 0 plus a half h bar omega psi 0. And now, if we look at this expression, remember psi 0 goes into a minus, and then the output of that goes into a plus, right? But we know what is a minus acting on psi 0. It's 0, right? That's how we set things up. So that's 0, okay? And then a plus acting on 0. It's a linear operator on 0, so it's 0. So this whole first term is 0, okay? So this whole thing is just equal to 1/2 h bar omega times psi 0. I could say psi 0 of x, right? So this number times psi 0, that is our E0. So now we figured out the ladder, okay? In this ladder of states, okay, the bottom is E0 is 1/2 h bar omega. And the corresponding state is psi 0 of x, which is the normalization constant times the exponential minus m omega x squared over 2h bar. Okay, and then as we go up the ladder, we get an energy that is higher. Okay, so the next step is 3/2 h bar omega, and then 5/2 h bar omega, and so on. Okay, and then we get a psi 1 of x, which is a plus acting on psi 0. Okay, maybe we don't know what that is yet, but we know what's the a plus operator. We know what psi 0, so we'll just let it operate and see what we get. Okay? And then psi 2 of x is a plus acting twice on psi 0. And in general, for state n, we get an energy En, which is n plus a half h bar omega, and we get a wave function psi n of x, which is letting the A plus operator act n times on psi 0. And that can keep going up for higher and higher n's. So this, formally speaking, is a solution for what are the stationary states and the corresponding energies. Okay? And so let's see, I'm shorter on time than I expected. In the next class on Thursday, I will put this into Mathematica, and I'll show you how I have Mathematica code to do the operator A plus, okay? And then I can let A plus act as many times as we want and bring us to higher and higher states going up this ladder. And then we can see what the functions are. Right? But now at least we do see what the energies are. We see that the energies are equally spaced, unlike the particle in a one-dimensional box. And we see there's a certain non-zero energy at the bottom. Okay? And there is a word for this energy at the bottom. The energy at the bottom is called the 0 point energy. And so this is telling us that in quantum mechanics, unlike classical mechanics, the lowest possible energy state is not energy equals 0, right? For a classical harmonic oscillator, you might have a particle that's right at x equals 0 and it's not moving, right? It's just sitting at the bottom. And so it has 0 kinetic energy and 0 potential energy, so 0 total energy. Okay? But in quantum mechanics, that's not the case. Right? In quantum mechanics, even at the bottom, there's a little bit of energy. And so you have a little bit of potential energy and a little bit of kinetic energy. And that kind of goes along with the uncertainty principle, right? The uncertainty principle would say there has to be some uncertainty in the position and some uncertainty in the momentum. Okay, so that means a sum x squared, a non-zero x squared, and a non-zero p squared. Okay, so a little bit of kinetic energy and a little bit of potential energy, and that's consistent with what we are calculating here for the 0 point energy. Okay, so this is really, the essence of what I would call a trick solution, right? That, I did all this stuff with operators and then somehow it just kind of unexpectedly turns into a solution for this problem. Of course, I didn't make up this solution. I don't actually know who made up this solution. But, it's remarkable that it works. It's really kind of amazing that it works. And it really is less work than the sort of standard approach to solving a differential equation, which involves, how do you put on the boundary conditions at infinity and make sure the function doesn't go to positive infinity or negative infinity, anything like that. That's the analytic approach, which you can read about in the textbook for comparison. Okay, so I'm going to stop here, and then the class on Thursday is going to be mostly in Mathematica, showing you what these wave functions look like. And then we can talk about, what if you have some initial condition and how do we get the general solution given a certain initial condition? Okay, so I'll do that on Thursday. Okay, so let's maybe take a break for now, and I'll see you guys then.